Are you preparing for AP Physics or SAT Physics exams? If you are serious about doing well, get a tutor to help you understand the key concepts in physics. I can help you understand physics intuitively. It's actually fun and easy. Let us try some problems together. Go to College Board's website and open AP Physics course description.pdf. Try these problems on your own first, and then watch my explanation. Number 1. In this problem, we're given the horizontal velocity and the height of the cliff, and we're asked to find the time that the object takes to hit the ground. Okay, well, let's draw this first. Here's the cliff, and the vertical velocity and the height is drawn in like this. And the projectile is going to look something like that, and we're asked to find the time. In this problem, VH doesn't matter, the horizontal velocity does not matter, because we're focusing on the vertical movement of this object. We're going to use this equation. This is the distance equation with the time involved. Y minus y naught is just the height, 125 meters in this problem. And the initial velocity in the y direction is initially 0. So we're given with 1/2 gravitational acceleration times t. 125 meters is equal to 1/2 times 10 meter per second squared multiplied by t squared. So we just use the math here to find that t is 5 seconds, and that'll give us the answer of B. Number 2. This is a graph problem, and we're given position versus time and 5 points along the curve, A, B, C, D, and E. Then we're asked to find where the acceleration of the particle is the greatest. Well, to go to an acceleration versus time graph from position versus time, we have to take the derivative twice. The first derivative will give us velocity versus time. And to find the curve of velocity versus time, we have to look at the slope of position versus time. AB, the slope is going down, which is a negative slope. At C, slope is 0. D and E, slope is positive. So we start out with some negative number for velocity versus time, approach 0 for C, and D and E is positive. Now from this graph, we can go to acceleration versus time. We have to look at the slope of velocity versus time, and it looks something like this. You have to practice this well to perfect how to work on this. So at AB, the slope is 0. There's a spike at C. Then at DE, the slope is 0 again. So the answer is C. Number 3. This is an inclined plane problem where we're given some kind of a mass and also the initial velocity at 0 and the distance down the incline, which is 20 meters, and the height, which is just 10 meters. We're asked to find the net force on the block, and to do that, we first draw in the forces on the diagram. Then we draw the force diagram, which is just a tidied up diagram of all the forces acting on the object of interest here, which is just the mass on the incline. And the acceleration is pointing down the incline, which is just pointing to the right in the force diagram. In this problem, we have normal force pointing up and the gravitational force pointing slightly to the right of the y-axis. And now we do a bit of vector manipulation here. We're looking at the y component of mg and the x component of mg. Because this object doesn't move up or down the y-plane, the normal force is precisely the y component of mg, which is mg cosine theta, and the x component is mg sine theta. If you have any questions on trigonometry, we can review that, and once we do the math, it comes out to be just 10 newtons, which is E. Number 4 is the same problem as number 3, except this time they're asking for the final velocity. Since we're given the distance down the incline and we know the acceleration from number 3, we use this equation, Vf squared equals V naught squared plus 2AD, and we plug in the numbers, and we can just do the simple math and get V final as 14 meters per second, which is C. However, if we didn't know the acceleration from number 3, we could also use work. Conservation of energy says that the initial energy is equal to the final energy of the system, and initially we started out with some gravitational potential energy, MGH, and supposedly all that energy is transferred to kinetic energy, 1/2 mv squared, and we're going to do some math over here, cancel the m's, plug in the numbers, and the final velocity is 14 meters per second again. Number 5. This is another force problem, just like number 3 and 4, where there's a mass on a tabletop with some horizontal force and some vertical force. Now, as we did before, we draw the gravitational force and the normal force on the object. Then we're asked to find the frictional force given the coefficient of kinetic friction, and we use this equation F equals mu k times n. So we have to find out what n is, the normal force. Well, to do that, we use the equation F equals ma. Sum of all forces in the y direction has to equal 0 because it doesn't accelerate in the y direction. So we have normal force minus the vertical force, 15 newtons, and the gravitational force. And if we plug everything in and do the math, normal force is just 35 newtons. At this point, we can plug in the coefficient of friction and multiply them to get 7 newtons. So the answer is E. Number 6 is a very easy, classic momentum problem where we're given two masses running head-on as our initial condition. And as our final condition, we have these two masses kind of getting clumped together and moving together at some final velocity. And the conservation of momentum says that mass times velocity of each of these masses have to equal the final mass times final velocity. In this case, the equation sets up like this. When we do the math, the left side, the initial condition, actually comes out to be 0. So the only way the final condition can be 0 too is that the final velocity is 0, and the answer is A. Number 7 is a torque problem. We're given a rigid rod with a pivot and two forces at points V, W, X, and Y. So we're asked to find what the third force has to be for there to be an equilibrium, which means that the total net torque is 0 for the system. In this problem, I'm going to set clockwise direction as positive and counterclockwise as negative. When we sum all the torques together, the force at point V becomes Fd, and the force at point Y becomes negative 2Fd. The third torque, shown here by a blue circle, has to be Fd in order for the system to be in an equilibrium, which just means that the sum of all torque is 0. At this point, we can just apply force F to points V, W, X, and Y and see if they give us Fd as an answer. And when we applied force F in the positive direction, we actually got Fd, so V will be an answer, and the negative direction is negative Fd, so that wouldn't work. If we apply force at the pivot, the answer is just 0, so that does not work. When we applied upward force, it was negative Fd, so that doesn't work. However, when we applied a downward force, that gave us a positive Fd, so makes X an answer as well. When we applied force at point Y, up or down, gave us 2FD in magnitude, so that didn't work. So the answer is V or X, and you can mark C as your correct answer.